I think I lost track of time. I think we can begin. Welcome back everyone. So we have a couple announcements for today to get it started off, but nothing too major. I think the probably most eye-opening one is it's already a week 11 out of a 15 instructional week, 16-week semester in total. So we really don't have a whole lot more time to go with this class. Pretty much what's going to happen is we'll finish off chapter 9 with this additional exercise at 9.3, just to get more practice doing a confidence interval. Then we'll switch gears and talk about hypothesis testing. Here, we're still going to be dealing with categorical data, exactly two outcomes, success versus failure. We'll be testing a hypothesis about the population characteristic P. After that, we'll turn over to chapter 12 and redo the confidence interval hypothesis testing, but we'll be doing it with a quantitative variable. So we'll see things like mu's and sigmas in that new setting. But that's pretty much the plan for the rest of the semester. We'll take our time to make sure we have enough time to get these done carefully. And for what we have going on today, beyond that, it'll just be our quiz number 10 that's due today. And just a reminder also, I'll be mass emailing the whole class just so we see it again in the email. Since tomorrow's Halloween and we are officially a night class, we're going to cancel this one because we're in a good spot in the schedule. There's no reason to try to rush through anything. We have extra time. So that's the plan so far, folks. Any questions or comments at all before we get started? Okay, let's practice this procedure just one more time. The formula here is also captured in multiple formats, but just in case you like the formatting here, let's take this as a screenshot and put it on our notes as we go to solve this question here. Probably doesn't have to be that big. Let's shrink that down. And this will be our first problem to start us off. It says, for the context, the technology underlying hip replacements has changed as these operations have become more popular. And they say next, starting in 2003, highly durable ceramic hips were marketed. And they say, unfortunately, for too many patients, the increased durability has been counterbalanced, that's probably a pun right there, by an increased incidence of squeaking. So that's the scenario so far, and it sounds kind of funny in a way, but you can imagine that's terrible. You use your hip a lot, you don't want to hear it squeaking every single time that happens. This could drive people insane, and so there's a lot of angry customers out there. And that's what this article is addressing. So this is a real article from 2008, published in New York Times, and they reported one study found of 143 individuals who have these hips, found 10 hips develop squeaking. So we want to see, based off this evidence here, what is the true proportion or true percentage of all of these ceramic hips made in this time frame that would develop squeaking? So that's our context. Let's go through it a second time and see if we can pick out any numbers. I think pretty much all of this was pretty much just a huge set of context for us to think about. So the 250,000, really not necessary for us in this problem. But it got interesting once they started talking about the 143 individuals right here. That looks like a sample size, so let's call this n equals 143 to start out. And this always looks pretty bad, but this is the successes right here, developing squeaking. It's kind of weird because it's not a good outcome, but it's the outcome that the study is interested in, how many ceramic hips went bad. So say here, let me write this differently. There are number of successes equal to 10 coming from right here. So if we have a sample size and a number of successes, we should be able to run through this entire procedure right here. Any questions at all, folks, about getting those two values out? Okay, next thing is part A. And part A, I'd probably just reread the whole problem again to get a feel for it, because there are a lot of moving parts with these kinds of things. It wants us to describe the unknown parameter or population characteristic. So we can begin by just automatically calling it P. Since we're dealing with categorical data, and we can say it's P equals the true proportion of something, and I pretty much like to put this here on paper since it's always pretty much going to start off like this. If you indicate a value P for your population characteristic or parameter, But now we have to say it's the true proportion of what specifically? Has anyone spotted what we're looking for in this problem for P? Exactly. We could say the true proportion of these hips that squeak. I put right here, I'm going to undo this highlighting for a moment, but I said these hips to count for ceramic hips marketed specifically between 2003, 2005. Like we mentioned before, sometimes you can let some of the context be carried by the actual wording of the problem itself, but we did have to bring in the context, mention hips because we're talking about a hip replacement, and mention the bad thing that they're developing squeaking. I would say those would be the two things we would have to have here for a good definition of that unknown parameter P. So now that we have that, we can proceed with the rest of the problem, and it's really just a matter of kind of like doing the 1.5 IQ rule of thumb, put down the right formula, substitute in the right information in these spots, and you'll have your full confidence interval. Well, let's go off to our part B here. It wants the sample proportion of successes. And because it said sample proportion, we'll start off with a P hat. These symbols are always a really good idea when you write them down on these questions, because it's reminding us that it goes right here once we make that computation. So you'll notice in the notes, every time you had to calculate something, I always start off with the name of the thing we're calculating, put down an equals, and then now we can put in the value. It's always going to be the number of successes in the numerator, following right up here with the red dot. So we identified 10 successes, that was 10 hips that began squeaking. Divide by a sample size n, that's the value right here. But we also indicated 143. And so that's our sample proportion of successes so far. We just put it in a calculator and rounded this one to 4 decimal places. So we've got lots of stuff from last week. Let's just clear that out. 10 divided by 143 gives us a sample proportion of successes at about 0.0699. The 3 to the right is going to cause it to round down to 0.0699. And so already we can say about 7% of the sample contain hips of these kind that will develop squeaking later on. And now we're wondering, amongst the entire population, how much is it going to be? This is going to be our best guess if we're putting down one number, but a confidence interval will be much better than giving that one number. We'll be able to say the error in our guess as well. What, any questions so far, folks, to this stage of the process? Okay, let me grab our formula up here. Let's maybe park it down in part D for the moment, just so it's out of the way. Next thing we want is the standard error. And when you see this object right here, we do have to be careful because there are multiple formulas for standard error. It just depends on which chapter you're in. But if you calculated p hat, then the formula that we're going to use goes like this. The standard error of p hat is going to be the square root of p hat times 1 minus p hat, divide by that same sample size n. So there's that standard error formula again. We calculated this quite a lot. We'll do it quite a bit more as we go through the rest of the class. And then once again, we're just dropping in values. So the strategy is definitely call it SEP hat, because that will remind you that this plugs in right here when you get to the end stages. After that, it's a really, really good idea to just write down the formula. It helps us become familiar with it. You'll probably memorize it after several problems. And also, the main purpose there is, now we can look up things like the n value, the p hat, and know exactly where it goes as we start writing it down the next step. So for p hat, put in 0.0699. They'll go right into that location, times 1 minus the same value. Then next step, divide that entire thing by sample size we found. Up here, it's set to 143. And so now we're ready to calculate this right here. Any questions or comments first, folks, on writing down this statement here for standard error? Okay, good news is this is essentially, like we mentioned before, almost all the partial credits right at this dead. So even if I completely mess it up in the calculator, that's okay. You would never be docked a whole bunch of points, not even on a quiz, definitely not on the exam, not the final exam. So back over here, still, it's a good idea to get it in right, especially for web assigned, so let's be careful. We've done this in a number of ways where we just type it all into the calculator and run with it. For folks that feel like you've got this down, but you might want to try it an even faster way, here's another approach. You can type in the value 0.0699 and just hit enter. Now I'm going to type in this thing right here. So second, this button right here calls up the square root. Let me make that a little bit bigger. And now instead of typing 0.0699, I'm going just to refer to it. You can use up arrow, hit enter, and it throws it in there. A parenthesis, 1 minus, that's just copying the formula. Then up arrow and enter, brings it right back down again. Close that parenthesis, divide by 143. And to me, that's probably about the fastest you could ever calculate that. The value I'm getting on this is 0.0213. It would round down to 0.0213. Yeah, go ahead. To get it to carry in, it kind of went like this. Let me go back to 0.0699. So type it in once. Oh, and it varies on calculator. So let me know about how it looks in this step. So once I go to the square root, what I did was I up arrowed and hit enter. But on your calculator, when you up arrow, does it highlight up here? No. So instead of that strategy, try this strategy out. Hit the second key and the enter button. Oh, what did that do? That just killed it. Let me try it once more. Second and square root. Second and, oh, this is what I want right here. The A and S button right here calls in the prior answer, 0.0699. So this is another way that should work. So parenthesis, 1 minus, hit the second key and the negative sign again to pull in the prior answer. Divide by 143. And, oh, did we get the same value? I think we did, 0.0213. Yeah, I somehow remembered that number. Is that what you're getting in your calculator? Yep, you betcha. It's not a huge timing saving step, but you can imagine if this was like 12 digits long, that is a good timing saving step. And it's also really good for accuracy because if I'm typing in 12 digits, I'm probably going to mess that up with a high chance. So either way we do it, we get a 0.0213. Let me record that result. And any questions at all, folks, on getting that number? Okay, there's definitely multiple strategies. And again, I showed it several different ways, but I'm not encouraging anyone to do it a specific way. It's more for whichever way it looks like it works the best for you. I'd say stick to that. So going back to the problem, we're just about ready to calculate the entire confidence interval. We have p hat, we have the standard error over here. All we're needing is a critical number, and we'll know what to use once they tell us the level of confidence in the problem. But part D is asking for something different. It's wondering, are the conditions even met for the large sample confidence interval? That's a great question. Let's go up above. And first thing I'd look for is any information they might give us on randomization. Here it says, New York Times reported that in one study of 143 individuals, 10 of them developed squeaking. All I know is this came from a study. They didn't cite the study. I don't know if it's a random sample or not. Let's all say what we did before in the prior problems. We just don't know. So I'll say here, it's, oh, and I always used a different color pen. Only because this is not the major part of the conditions, but it's still something we should write. I'll say here, it's not known. If the sample was random, let alone representative. We just don't have that information. Doesn't mean it wasn't. It might very well have been a nicely, very carefully planned, simple random sample, but they just didn't tell us. So that's how we addressed that part of the information. The next thing we have to have is for the central limit theorem to actually give us accurate probabilities, we go to calculate the critical number Z star. We're using the normal curve for that. We had to have a certain number of successes and failures. Both of them had to exceed 10. And looking right here, we barely made it. There's 10 successes right here. But actually, our author's rule is conservative in the sense that right at 10, we're still highly accurate in most contexts. So let's say here, to finish off the rest of the problem, the number of successes is 10, and that always looks weird. It is greater than or equal to 10. This is just me double checking it actually meets the benchmark of exceeding 10. So I'll just write it that way and just put a check to say I'm happy with that. It did exceed 10. And we can say below, and the number of failures is, we can do this in this kind of way. Take the number of successes, combine it with the sample size, and we can go n minus 10, put in the value of n, it's 143 minus 10, to get to 133. Again, that's definitely greater than or equal to 10, so we meet that benchmark for the number of failures. And I definitely ran out of space. It's good to say one last thing. Let's say here, because we exceeded 10 on both successes and failures, and so the sample size is large enough. So that's the one thing we can verify in these kinds of studies. They have to tell us the sample size. They have to give us a notion of successes in the problem. And so that's something we'll always rigorously check in these problems. The portion right here, though, I'd say it's kind of easy to miss. So let me put an arrow just on this line. Now let's say, don't forget the conclusion. What I mean by that is, when you work at this kind of problem on checking conditions, I'm not as worried if you didn't put this here. That's a hard condition for us to check, unless they just strictly tell us it was a random sample. But once you go to do these computations, it's not enough to say greater than or equal to 10 on both of them. We also have to say what it means, and it means the sample size is large enough. So don't forget that last sentence. It's really, truly easy to miss on these kind of problems. Okay, so we've done most of the main computations. Here's p hat, here's standard error. Now we're finally going to do a 95% confidence interval. Any questions, folks, before we give this last portion a try? Okay, let me grab this information. This is where I would be looking to finish the last of the problem. So, and that's supposed to be the enter key, put all this down below. Next thing I would do is definitely copy down the formula for the confidence interval. We have it cited right here, and it goes p hat. Oh, let me change colors. Plus or minus our critical number, which is given as a z star. I think we used a different color. Let me make it about the same. Multiplied by the standard error of p hat. So that's the thing we're going to be calculating next to finish off the confidence interval in part E. Once we do that, we're pretty much done. We'll just have to interpret the interval. So we're done with these formulas right here. I'll just leave it on the end of the notes as a reference at the very end of this document. Now let's come back up here and calculate all these unknown values. We already have p hat, we already have the standard error, so it's now just down to z star. And if you've done enough of these, some people might have this even memorized. That's kind of amazing. Anyone happen to know what z star would be in this problem? Good call, exactly 1.96. This is actually rounded to 4 decimal places, so it's even more precise than it looks. And if you're not sure what it would be, this is exactly what I would do right here at this time, and this time right in part E. Let's go to the Moodle website. It's now just a huge reference, essentially. Go to, not that one, don't go to that one, go to the original notes, section 9.3. It shows the central limit theorem Standard error, that's really our major way of building the confidence interval. But then right here, this is the information you want. That's so important. Let's copy it once more. Along with the information, definitely an important table to return to. If I was taking the third exam or the final exam, I would always bring this on my notes. Otherwise, you'd have to calculate from scratch. It's not terrible, but that's an extra thing you wouldn't want to have to do on an exam. Let's put it maybe right here. So the 1.96 came only because they told us 95% confidence. So that's the value we cited. So now up above, we're just about ready to finish this off. We're going to go left to right, substituting in values. First one is p hat. So go down, it's a 0.0699. Then add and subtract our critical number. That's right here at 1.96. That whole thing gets multiplied by standard error, which is down here or up above, 0.0213. Final thing to do is calculate the lower bound and upper bound, and we'll be just about done. So I think we can eliminate this information. But any questions so far, folks, to this stage? Okay, so here it's more of a just kind of a relaxing math problem at this point. We're through the worst of it. And whatever is on your paper here, even if we made a mistake doing a computation, again, as long as it looks like this on paper, you've got essentially all of the credit. So 0.0699 to start. It's a good idea to do a lower bound first, since the confidence interval is always started with the lower number and then the higher number. So let's go minus 1.96, parenthesis 0.0213, and that should be our entire interval. So first value we get, let me double check. This time we're rounding to 3 decimal places. Now that we're at our final answer, it came out as a 0.028. So let's put in 0.028. I'm going to write this in inequality form because it's always a good idea to emphasize the actual thing you were building the confidence interval for. If you use an ordinary interval, a comma would go in the position where these parentheses are, or excuse me, these inequalities are. And you would just state the lower bound and the upper bound. But here we're emphasizing that's the thing we estimated. It's larger than 0.28. And if you hit second and the enter key, you can recall this last line and switch it to positive right here. Now we've got an upper bound. Hey, this is the first value so far in class that rounds up to 3 decimal places. Take a look at the fourth. That's above 5, so we'll go 0.112. So we did it, folks. That is our 95% confidence interval in total. We still have to interpret all of this, but we pretty much have the whole setup ready to go for a fast interpretation. Any questions at all, folks, to get to this stage? Okay, so here's what I would take a look at as soon as it says practical interpretation using the context. You definitely want to pull down whatever you said in part A. Even if that was a mistake, that's okay. Just maintain what you said here, and you never get double jeopardy on these kind of points. Okay, so we'll park P right here. We'll take a look at this interval, and this is essentially all we have to say. Oh, let me scroll up just a little bit. We absolutely have to say the amount of confidence we have. Not saying that is like taking away the percent chance when we interpret a probability. It's probably the most important thing we have here. So we'll start off by saying we have 95% confidence that, then we change gears and start talking about the unknown population characteristic, P. In part A, we said it is the true proportion of these hips, ceramic hips manufactured in like 2003, 2005, I think, that begin squeaking eventually. But we'll just say it this way, that the true proportion of, here, only because that's good to emphasize, I'd probably want to put in this word, It's not something I take points off of, but because we're talking about a population characteristic, we're also talking about a population. So saying all just helps us emphasize that. We're talking about all members in that population. So the proportion of all these hips that squeak, then we come up here and just say is between 0.028 or you could say 2.8%. I think that's probably the better interpretation, but if we start with proportion, we should say proportion here. If you said percent right here, I think that's a good way to go. It'd be a good idea to put 2.8% here to match up the units. Not too picky about that, but I'd say that's probably the better answer for interpretations. Here, I'll just stick with it between 0.028 and 0.112. So taking another look at this, p hat is right here at 0.0669, about 7%. And notice it's right between these values. It's right smack between it, in fact. If you took 0.112, add to it the 0.028, divide that answer by 2, you get the 0.07 right back. So in these confidence intervals, the statistic p hat is dead center. Then we did a movement to the right, 1.96 times the standard error. We subtract some values from the left, same quantity, but subtracted. So now we have a lower bound and an upper bound. And this value right here, that 0.07, that's just the best estimate of what's in the middle, p itself. But it could range as low as about 3% to around 11% altogether. So the margin of error on this thing is huge, but at least we have some estimate on what the true percentage could be. Well, any questions at all, folks, on running through this last confidence interval procedure? Okay, well, congratulations. I feel like this is a pretty tough one to just get right out of the gate as our very first statistical inference procedure. Now that we've gone through it, all the other procedures we're going to take a look at, they're not too dissimilar. For example, once we go to chapter 12, this is a bit of a preview, so we should say that right here. For the preview in chapter 12, here's how we're going to calculate the confidence intervals there. A 95% confidence interval. I'll often say CI to stand for confidence interval. For mu, this is the population's mean or the population's average. Now it's a different population characteristic, is of the form. It'll go, instead of a p hat, we use a different statistic. This time we're estimating the average of a population, mu, and we use the sample mean. So we'll go x bar in place of the p hat. We'll add and subtract a critical number. This critical number does not come from the normal distribution like z star comes from, but it comes from a distribution that's highly, highly related called a t-distribution. So we'll put a t star here. The way we calculate that probability and get t-star values out is very similar. And then multiply that whole thing by a standard error. But it won't be the standard error of p hat. We don't have that statistic. We'll do the standard error of x bar instead. So that's a different confidence interval, but the way we put it together is entirely similar, and even better, the way we interpret it is similar, completely similar. We just have to talk about the fact we're not saying proportion, we'll say average or mean instead. But now for the moment, we're still working on categorical data. We're going to switch gears from the confidence intervals to the hypothesis tests. We'll see that as well in chapter 12 for the quantitative data. Well, any questions at all, folks, before we take a look at what in the world hypothesis testing is all about? Okay, let's give it a try. We're now officially in chapter 10, so congratulations. That means there's just 2 chapters left of the entire course, chapter 10 and chapter 12. And this is how our notes on hypothesis testing starts. It starts with a huge bag of mysteries. It says, A hypothesis test uses sample data to choose between two competing hypotheses about a population characteristic. Now, when they say population characteristic here, let's say what they mean. This means we are testing either P, the population proportion, just like we did with our chapter 9, doing a confidence interval, or mu, a population mean instead. So that's what we're meaning by population characteristic. It'll either be for P or mu, and we'll describe the test for both of these parameters, starting off with P primarily. But then they said that there's two hypotheses, and this is what they mean. They are competing, they're completely opposed to each other. One is the negation of the other. We'll have the null hypothesis and an alternative hypothesis. A null hypothesis is a claim about a population characteristic that is initially assumed to be true. This statement right here turns out to be, I mean, they didn't say much, but that's a huge portion of the hypothesis testing already. We assume a null hypothesis is true. Let's highlight this here, but we'll come back to that and show where we used it. The competing hypothesis, denoted by called the alternative hypothesis, written HA as opposed to H naught, and it's the competing claim. So the best way to think about these hypotheses is just do an immediate example. If you ever watch shows like Law and Order, good news is this is the real thing in the legal system. We're doing the exact same kind of thing whenever we're doing hypothesis testing. The same format of logic is applied here. So the best way to think about this is, let's do a scenario. Let's say here, because we're doing an analogy on the court of law, let's assume something bad happened and someone's really guilty. Let's say here, assume, I'll take the fall, assume Mike has been caught going 98 miles per hour. This would probably destroy my car. In a 45 mile per hour work zone on I-15. I don't ever do that. I've never seen anyone get pulled over for that, but you can imagine the fines are stiff. They warn you about this all the time. Let's say here on camera. So they have my vehicle recorded doing that speed, license plate and all. So what you can imagine is going to happen, you're going to get a huge, huge ticket, but you will have the rights. You always have rights to go to traffic court and contest that ticket. A lot of people do that just in the hopes that the officer didn't show up that day, so you get let off scot-free. I don't know if it really works that way at all. But this is what's going to happen finally once you're in traffic court. So in traffic court, if they really want to nail me for this ticket, they're going to start thinking in these terms. There'll be a null hypothesis. We'll write H sub 0. I'll often say H naught for null hypothesis. The naught in H naught is the 0 there. And they'll set up an alternative hypothesis, HA. So that's the setup so far. And no matter what, whether it's hypothesis testing in a statistical problem or in a court of law, the null hypothesis is this. Mike is not guilty. Then, as the actual court proceedings proceed, that's assumed to be true. The null hypothesis is literally assumed to be true in a court of law. And that's why we always say things along the lines of, you are innocent until proven guilty. In other words, we assume you really are innocent. And everything we say and do in the court of law is with that understanding and that assumption. So we immediately, after forming that hypothesis, do the following. We immediately assume H naught is true. That deserves an exclamation mark because this is the part of what makes hypothesis testing really weird. We're not saying we know it's true. We're just saying, under the assumption that this is really true, how are we going to reconcile this with the evidence that we've amassed? Now, they're going to perform a competing statement down below here. The null hypothesis and the alternative are completely opposing statements. And so this one goes like this. If Mike is not guilty in the null hypothesis, in the alternative, Mike is guilty. There's an exclamation mark because as the statistician in this problem, you are the one who's trying to show HA is true. Think of yourself as the prosecuting attorney in every single one of these problems, and you've got the right mindset. Even the prosecuting attorney, with everything he or she says and does, that attorney has to assume the defendant really is not guilty. They're just going to say, well, under the assumption that Mike really did speed, how in the world did I get this evidence? And maybe play the video of me blowing past the work zone. So our goal is to show that the alternative is true and gather evidence for it. But in statistics, this is how we're going to make this happen. We want to show HA is true. And we will use probabilities as evidence. So in other words, we might say something along these lines. Let me type this out so we can just have it actually written down and not just contained in the video. So in the court of law, they're going to immediately assume that the H naught is true, that there's really no speeding going on when I walked in through that room. But then they'll show all the evidence, and we'll suddenly have a huge problem once we look at the probabilities. So here's how it will go. Once the hypothesis test starts, we will present evidence. For us, again, that's going to be probabilities, and make this argument. If H naught is true, and the probability is very small, we will say it is unlikely that H naught was in fact true, and that we have evidence in favor of HA. The alternative competing hypothesis. So said a different way, going through the court of law, they might say, well, the probability of Mike actually not being speeding, the null hypothesis is true, and I'm not guilty of speeding, but we found all of this evidence here, that probability is 0.003. There's only 3 chances out of 1,000 that Mike could be not guilty, but we found that evidence. Because that probability is so small, the null hypothesis is looking unreasonable, and we have support in favor of the alternative instead. So in other words, the evidence we're looking for is a probability that is small, very small, and we'll have to say what we mean by very small as we go through these problems. Very small probabilities are in support of the alternative hypothesis. Any questions about that so far? Okay, now here's maybe the trickiest thing about hypothesis testing when we go to make a conclusion. Suppose they didn't find that evidence. Maybe the value here for the probability, it was large, it wasn't very small. A large probability would say, well, the things that happened are typical. There's no reason to say that the null hypothesis is false. So if I can't support the alternative hypothesis in a court of law, it doesn't mean we're supporting the null hypothesis either. Just because a criminal got acquitted in law did not prove their innocence, they just failed to prove that person's guilt, in other words. Here's how it manifests for us. When we do hypothesis testing, there is only 2 possible conclusions. And this is a big enough deal, we'll draw something on the page for this one. There will only be 2 possible conclusions. And this is the same for us. We can't write a conclusion that goes away from this list. It would be an invalid conclusion. The first one, let's put the thing that we want. We want to show the alternative is true, that the speeder was clearly speeding and should pay the fines for it. So conclusion one would be this. We reject H naught in favor of HA. What we would probably say in this case is we found evidence that Mike is speeding. In other words, Mike is guilty, and they have found that evidence. It should be strong evidence, and the probabilities when they presented it must have been pretty small. Thinking in terms of statistics. So that's a good case. We want to prove the alternative is true. That's the interesting question of the problem, but we can't always do it if we lack the evidence. And when we lack the evidence, this is the most unsatisfying conclusion in the world, but even our legal system is based off of this. It's the right conclusion, sadly. We, at the very, very start, assumed H naught would be true, just to see how unreasonable that would be when compared with the rest of the evidence. But if everything fits, if we can't reject the null hypothesis, this is what we say instead. We'll never say we found evidence Mike is not guilty. The court wasn't even trying to approach that. We'll say instead, let's call this conclusion two, just for the sake of parallelism. We failed to show HA is true. We would probably say this as a prosecuting attorney. We did not find enough evidence to conclude, they would say beyond a reasonable doubt or something along those lines in court. Here we'll just say to conclude, Mike was speeding, or in other words, is guilty. And that's kind of a dissatisfying conclusion even for the defendant, because that statement there is not saying you are innocent. We were not trying to test that. We're just trying to say, is your amount of guilt so severe that when looking at the evidence, there's no chance you could have been innocent. You had to have done it. We don't find that evidence. Well, we're just unsure any longer, and you just get acquitted. So those are the two conclusions. We absolutely want to go for this one, where we showed the alternative is true. Well, any questions so far, folks, with these hypothesis testing ideas? Okay, well, the way the notes go, if we continue to the next page, here's the author's reminder of the two possible conclusions. We'll mention this a lot since it's really easy to make a conclusion that says we showed H naught is true, but that's never the case in hypothesis testing. Our author reminds us of these facts right here. I like the way she wrote this. She says, in hypothesis testing, the only two possible outcomes are you reject H naught. There's convincing evidence that the null hypothesis, if H naught were true, the data would be very surprising. So we say, well, H naught is probably not true. It must be an alternative instead. This is the bad one. If you fail to reject the null hypothesis, we would say there is not convincing evidence against the null hypothesis. If H naught were true, the data is not surprising for H naught being actually true in that case. But when we go to actually write our hypotheses, here's how it's going to look. The alternative has three different flavors, which is kind of disconcerting, but we'll always know which one it is based off the context. And the null hypothesis is always written in this specific way. When we say population characteristic, recall we're talking about mu or sigma. Or excuse me, I said that in a weird way. This would be P or mu. P being the population proportion, mu being the population mean would go right here. Value they're hypothesized would always go to the right. In the null hypothesis, we're testing direct equality. And there's three different flavors up here. There can be a greater than, If there's a greater than here, we call this one a right tail test. If you have a less than here, we call this one a left tail test. And when you have not equals, this one's actually the special test. This one's special in a certain sense that, well, it's two-tailed. We're testing in both directions. Sometimes we might not know the actual hypothesized value. It could be more or less. So this one is a two-tailed test. And it's also, let's put in this special word, this is the default test. What I mean by that is we have to look for information specifically in the problem if we're doing a right tail test. The problem has to tell us. Or if it's a left tail test, it must be told to us somehow, some way in the context of the problem. We can't find any directionality, left or right tailed. We will always go to this one, the two-tailed test. And part of our goal in these notes is to decide which is which in running through these examples. We're getting a little bit low on time, so I think this is probably a good stopping point for us right here. When we come back on Wednesday after Halloween, we'll take another look at this information, the possible conclusions, and these notes will be all about setting up the tests. The next section will be the errors we can potentially make. Then 10.3 is kind of a warm-up. We'll do a hypothesis test there, but we're kind of doing it blind just for the sake of a preview. And 10.5 is going to be our big section, like 9.3. 9.3 is where we did all of our confidence intervals. 10.5 is where we'll do all of our hypothesis tests, start to finish. The hypothesis testing is a little bit weird. Our author has broken it up amongst many different sections, which I think is probably a good idea. It all comes back together in 10.5. Well, any questions, folks, before we call it a night? Okay, well, have a great one, everyone. If you're going to be outside tomorrow, be careful out there, stay safe. I'll see you all on Wednesday.